Hello there, Mr. Sutton here, bringing you the BC Calculus 7-8 Part 1 homework solutions on interval of convergence. On this problem, I'm trying to find the radius of convergence for the power series. My first question with this is, can I write this as a geometric series? It doesn't quite look there yet, but if I separate a 3 from this exponential term, so I write 1 over 2 times 3, then what I have left over in the other fraction, I have an x minus 4 to the n over a 3 to the n, which I can write as x minus 4 over 3, all of it raised to the n. So rewriting it like this, I see that this is a geometric series. We have repeated multiplication by x minus 4 over 3. So my geometric term, my r value, my common ratio, is going to be this x minus 4 over 3 term. So once I've got that, if I want to find the radius of convergence, I just have to take the absolute value of the common ratio and set that less than 1. And then I just have to put this in 1x minus a form inside the absolute value so that the thing on the other side of this inequality will be the r value. So to do that, I'm just going to multiply both sides by 3. Now that I've got this in 1x minus a form, I can just pick out my radius of convergence from the other side here, and that ends up being 3. So that's choice C. For this problem, we want the interval of convergence for this series. The first thing I notice about this series is that I have both parts of my fraction raised to the n power. So I've essentially got a geometric series here. I'm multiplying over and over again by pretty much x minus 1 over 3. So I can write that as my common ratio. And since I'm looking for the interval of convergence, I'm just going to take the absolute value of this and set it less than 1. Now I'm going to solve for x. So to do that, let me multiply both sides by 3. And then I can rewrite this absolute value equation or inequality as negative 3 less than x minus 1 less than positive 3. One more step, I'm just going to add 1 to all 3 sides to get x by itself. So I'll end up with negative 2 less than x less than 4. And since this is a geometric series, I know that I'm not going to converge at these two endpoints. I'm definitely strictly less than, no equals in here. So I can accept negative 2 less than x less than 4, choice C, as my final answer. For this problem, we're given this series that converges at x equals 7 and diverges at x equals 9. We want to know which of these statements has to be true. First thing I notice here is that I've got a center of x equals 4. So I'm going to write down everything I know for sure, then I'll take a look at these. So our center's at 4. That's 3 away from our first converging value of x equals 7. So that means that anything that's within 3 of x equals 4 in either direction is going to converge, just like x equals 7. So that means that anything that is between 1 and 4 will converge. So I know for certain then that things that are between 1 and 7 are all going to converge. In fact, I know that 7 is going to converge because they told me. I'm not as sure about 1, though. 1's one of those border values that could converge or diverge, so I'm going to leave no equals in there for now. All right, let's write down what we know about diverging. I know that I'm diverging 5 away from my center of 4. That means any values that are more than 5 away in either direction are going to diverge. So, for example, if x is less than negative 1, or greater than or equal to 9, I'm going to definitely diverge in those situations. And again, the only reason I can write greater than or equal to 9, but not the negative 1, is that with 9 they actually told us we're diverging there. So let's look at our options now. Series converges at x equals 1. Well, that's on the border here. That's on the fence. That could be converging or diverging. So that's a maybe, but it's not a yes. Next one, series converges at x equals 2. Well, 2 is between 1 and 7. It's closer to my center than my converging value of 7 was, so 2 must make the series converge. Next, series diverges at x equals negative 1. Well, that's on the border of this diverging, this other side of the diverging divide here. So that's going to be a maybe as well. Maybe it does, maybe it doesn't. We can't say either way, though. So then only answer choice B is going to work. Only option 2 is true for sure. On this problem, we want to know the interval of convergence for this series. So I'm going to rewrite this to make it a little easier to work with. Since these are both being raised to the nth power, I'm going to write this as x plus 2 over 2, all raised to the nth power. And I see when I do this that this is a geometric series. We have a repeated multiplication by x plus 2 over 2, so that's actually our r value for this one. Since it's geometric, to find the interval of convergence, I just take my r value, take the absolute value of that, and set that less than 1. Okay, now I'm just going to go ahead and solve for x. I can start this process by multiplying both sides by 2, so that gives me absolute value x plus 2 less than 2. And then I'm going to rewrite this using inequalities, so I can write negative 2 less than x plus 2 less than 2. Next, to solve for x, I'm just going to subtract 2 from everything. So that would be negative 4 less than x less than 0. And I know, because this was a geometric series, that I'm going to diverge at the endpoints, negative 4 and 0. I know this is strictly less than, not less than or equal to. So that means that I can choose answer choice A. For this problem, I want the radius of convergence for this series. To make this a little easier to work with, I'm going to rewrite this. I noticed that I have an nth power here and an nth power up here. I can actually rewrite this as x minus 2 squared over 3, all of it raised to the nth power. So kind of undistributing an n exponent over division here. So when I look at it like this, I've got this repeated multiplication. That means this is a geometric series, and we have an r value of x minus 4 quantity squared over 3. So in order to figure out radius of convergence for a geometric series, I take my common ratio, the absolute value of that, and set that less than 1. And once I've done that, I just need to put this in x minus a less than r form. So basically, I have to isolate this x minus 4 stuff in here. To start that process, I'm going to multiply both sides by 3, so I'll have a positive 3 over on the right. And now to get rid of this square, I'm going to square root both sides. Since this is absolute value less than, I don't need to write negative 3 because that would actually be false. Absolute value of something is never going to be less than a negative number. So I'm going to just write x minus 4 absolute value is less than square root of 3. And now I've got this in 1x minus a form. So whatever's on the right side here is my radius of convergence. So in this case, radius of convergence is just going to be the square root of 3, which is choice C. On this problem, we want to know what values of x this series converges for. First thing I pick up about this series is that I've got a geometric series. This 2 over x squared plus 1, this is all one big constant that's being multiplied by over and over again. So I actually have a geometric series with an r value of 2 over x squared plus 1. Since this is geometric, to find the radius of convergence and the interval of convergence, I have to take this common ratio, absolute value of this stuff, and set it less than 1. So absolute value of 2 over x squared plus 1 is less than 1. That's my starting point. And now I'm going to start solving for this thing. So to do that, I'm going to start by dividing both sides by 2 to get rid of this 2 here. So I'll have 1 over x squared plus 1 absolute value is less than 1/2. And now this is kind of a tricky situation. I'd really like to flip both sides of the equation, but there's a price for doing so. So if this left fraction here is less than 1/2, since I have a 1 in both the numerators, that must mean that this denominator, x squared plus 1, is itself bigger than this other denominator of 2, because if you divide by something bigger, you get something less than the other thing. So if I flip this and I write x squared plus 1 on the left side, I have to say that that's greater than the 2 that I have on the right side. And now I can go ahead and solve a little bit more for x. So subtract 1 and take the square root of both sides. So I'm going to have x, and this seems like it ought to be plus or minus 1, but what's really going on here, if x squared is greater than 1, that means the thing that I'm squaring, which I can find by square rooting, the thing that I'm squaring has to either be itself bigger than 1, or it has to be less than negative 1, so that when I square it, I get something bigger than 1. So I'm going to end up then with x is less than negative 1, or x is greater than positive 1. Both of these are going to solve this equation. So that ends up giving me, let's see here, answer choice D. For this problem, we want the radius of convergence of the Maclaurin series for this right here. So the key here is recognizing that this is in a geometric infinite sum form. Since this is geometric, to find the radius of convergence, I just need to get the common ratio and set that less than 1 in absolute value. So common ratio is going to be whatever I'm subtracting from 1 in the denominator here. So since I've got this in infinite sum form, that means my common ratio is going to be negative x squared. So I'm going to take the absolute value of that and set it less than 1. Since I'm absolute valuing it, I can get rid of that negative. And if I square root both sides, I'm going to end up with absolute value of x is less than 1, which means my radius of convergence is just going to be this 1 over here. So choice B. On this problem, I'm given this power series that converges at 5, and I want to know which statement about diverging and converging must be true. Let me start by writing down what I know for sure. I know the center of this thing is x equals 3 because we have x minus 3 inside this nth power parentheses. So center is at x equals 3. If I'm converging at 5, I know that I have a radius of convergence of at least 2. If I can go from 3 to 5 and get a converging number, then I'm at least 2 out in both directions from 3 is going to give me converging numbers. So that means I can write that I'm going to be converging between -1 and +5. Now I can't be sure about -1 because it's on the border, but everything between -1 and 5, and including 5 because they told us that converges, we can definitely be sure about those things converging. We can't be sure that this doesn't converge elsewhere. It may converge further out. They just didn't give us a point that was further out. But we're at least sure about what's in this interval. So with that in mind, let's look at our different answer choices. Choices A and B are talking about where this series diverges. The only way we could really talk about diverging based off this information is if they said it diverges, for example, at x equals 2. Then we could say, no, it doesn't. It converges because x equals 2 is in this interval. But since they're talking about where it diverges, we don't really know much about that. So we can't choose either of those answer choices. Now this next one, series converges at 1. Well, 1 is just as far away as 5 from the center. But even if it is an endpoint, we don't know for sure that we converge there. Endpoints can converge or diverge. So because it's not within the radius of convergence, it's right on the border, we can't pick that one. We can say that x equals 1 may converge, but then again it may not. For choice D, series converges at x equals 2. Well, 2 is between 1 and 5. So based off of being in the interval of convergence that we're sure about, we can say that yes, we do converge at x equals 2. Let's just check choice E to be on the safe side. Here we're seeing we converge at x equals 6. Well, 6 is outside this interval. It's bigger than 5. So although we can't say that it diverges, all we can see is that it may converge. We don't know for sure about 6. So choice D then is our best choice. For this no calculator free response problem, we have the function f defined by this power series here, and we want to find the interval of convergence of the power series of f. Okay, well, taking a look at this here, I see that we have a geometric function with an r value of x plus 1. That's what we keep multiplying by over and over again. So to figure out interval of convergence for a geometric series, I just take the absolute value of my common ratio, x plus 1, and set it less than 1. So for my interval of convergence then, absolute value of x plus 1 less than 1, I now need to solve for x. So I'm going to rewrite this with inequalities. I can write -1 less than x plus 1 less than 1. And at this point, just solving for x, I subtract 1 from everywhere. So this is going to be -2 less than x less than 0. Now I know this is the final interval of convergence because I have a geometric series. That means that the endpoints automatically diverge. So I can write less than here instead of less than or equals with full confidence that this is it. For this part of the problem, they're telling us that the power series above is the Taylor series about x equals -1. They want the sum of that series. Well, since again this is a geometric series, that means we can use our infinite sum formula for a geometric series to actually figure out the sum. So we need two things for this. We need the a1 value, the first value, and we also need the common ratio. a1 is pretty easy. Just look here, it's 1. It's the very first term of the series. For the common ratio, we figured that out in part A. That was x plus 1. So I'm going to be doing a1 over 1 minus r. In this case, that's going to be 1 over 1 minus x plus 1. And I could actually leave it like this. I don't have to simplify it. But if I wanted to, this is 1 minus x minus 1. 1's cancel, so you just have 1 over negative x for your final sum. For this part, g is a function defined as the integral from negative 1 to x of f. We want the value of g of negative 1/2 if it exists, or a good reason why it can't be determined. So for this, we look at the interval of convergence of f. We actually figured that out in part A. We found that it was negative 2 to 0. Since negative 1/2 is on this interval, that means if we use f to get to the value of g, we'll be on solid ground because negative 1/2 is on this interval. So at least f converges there. All right, so we need a better expression of f than we have up here with this power series. We're going to use what we did in part B now when we took the sum of the f series. Remember, that was negative 1 over x. And again, this applies because this is based off of the series here. This applies to f on the interval from negative 2 to 0. So at this point, we're just going to plug in negative 1/2. So we can say g of negative 1/2 is going to be negative 1 to negative 1/2 of the f function. And I'll put t's in here because we started with an x for this upper limit. So this is really just taking the integral of negative 1 over t then. Integral of that's going to be negative ln absolute value of t, evaluated from negative 1 to negative 1/2. Plugging these things in, we've got negative ln of 1/2. And then, let's see, we would have minus ln of negative 1, which is really just minus ln of positive 1. Well, ln of positive 1 is just 0. So this goes away. Ln of 1/2, if I have a negative out in front, I can actually pop that in as a negative 1 exponent. So this is really just ln of 2 we're dealing with if you really want it to be fancy and simplify it. So there you go. On this last problem part, they're saying h is defined as f of x squared minus 1. They want first three non-zero and general term of a Taylor series for h. Then we're going to use it to find h of 1/2. Okay, well, let's start by figuring out what h looks like algebraically. H is just f with x squared minus 1 as the input. So I'm just going to go up here to the f series and plug in x squared minus 1 wherever I see an x. So I've got a 1 to start with, nothing new there. But now I'm going to plug this in red so you can see it. I'm going to have x squared minus 1 plus 1. Next, x squared minus 1 plus 1 squared. And then x squared minus 1 plus 1 to the n, and so on and so forth. I can simplify this a bit. This is going to be 1 plus x squared, because those 1's in there cancel out. This is going to be x squared squared, so x to the 4th. This is going to be x squared to the n, so this will be x to the 2n as our general term. And we've met this part of the problem. First three non-zero terms and the general term. Okay, next they want us to figure out h of 1/2. Now notice they didn't want us to approximate h of 1/2. They want us to find the value of h of 1/2. Since we're representing h as an infinite series, that means we have to add this whole series together. Okay, well, this is actually a geometric series. We have an a1 value of 1, an r value of, let's see, we're multiplying by x squared each time to get the next term. So we're going to go ahead and plug this into our infinite sum formula. I can write, in general, a1 over 1 minus r is the sum. So in particular, h of x is going to be my a1 value of 1 over 1 minus my r value of x squared. And now to figure out h of 1/2, I just have to plug 1/2 into this for x. So that's going to be 1 over 1 minus, this is 1/4 down here. So 1 minus 1/4 is going to be 3/4. Since that's in the denominator, I can just multiply by the reciprocal, same change flip. So 1 times 4/3 ends up giving me a final answer of 4/3.